Okay, so our second speaker of the session is Dr. Luke Duncan from the University of Warwick in UK. So Luke, do you want to present yourself before I share your presentation?
Sure. I'm Luke Duncan. I'm based at the University of Warwick in the United Kingdom. And the presentation that I'm going to be giving, well, that you'll see now is basically looking at a meta-analysis of environmental enrichment in primates in captivity.
So let me share your presentation. Wait. Sorry for this. Share screen. Okay, it's here. Here.
Hello, I am Luke Duncan, and I will be presenting on the findings of a meta-analysis that I carried out with my colleague Neville Pillay. Our talk is entitled Just Toss in a Toy, a meta-analytic appraisal of captive primate environmental enrichment. Hello, I am Luke Duncan, and I will be presenting on the findings of a meta-analysis that I carried out with my colleague Neville Pillay. Our talk is entitled Just Toss in a Toy, a meta-analytic appraisal of captive primate environmental enrichment. Environmental enrichment can broadly be defined as any intervention in a captive environment which is intended to improve the welfare of animals. It might take a variety of forms, ranging from adding new features or space to an environment to modifying the social environment, or even providing cognitive or improving welfare, and there is a substantial amount of evidence that enrichment is generally very effective. However, this is not always the case, and enrichment practice has received some criticism in the scientific literature. The main issues with enrichment are that it doesn't always work. It is typically applied in a trial and error fashion. There is the assumption that if an approach has worked in one context, it will work in all contexts, and that the interpretation of the findings is often subjective, reflecting the interpretation and opinions of the authors themselves. It has been suggested that a more predictive approach to enrichment is needed in order to move the science and practice forward. It requires that we identify those enrichment practices that are successful or unsuccessful and try to determine what underlying factors might predict the success thereof. With this in mind, we sought to carry out a meta-analysis in order to appraise the current enrichment practices for captive primates as reflected in the scientific literature. Specifically, we wanted to identify those enrichment practices that best enhance welfare of primates generally, and to develop and apply a metric of enrichment efficacy which would be comparable across a range of different contexts. We hope that in doing so, we are laying the groundwork for a predictive approach to enrichment practice by identifying effective enrichment, highlighting those areas which are poorly understood, and providing a tool for the comparative assessment of enrichment effects. We started by using a Boolean search phrase, which included the terms primate, environmental enrichment, behavioral enrichment, and behavioral engineering, with behavioral enrichment and behavioral engineering being synonyms for environmental enrichment that are sometimes used in the literature. In order to streamline the search, we specifically targeted those databases which included journals that publish literature on captive animals and primates. These included Bio1, the DOAJ, EBSCOhost Academic Search Complete, Ingenta Connect, the Oxford Academic Journals, Science Direct, Springerlink, Taylor and Francis Online, and Wiley. We also included the journal Animal Welfare, which was not archived in any of these databases. In order not to limit the range of possible articles to include in our sample, no lower date limit was set, and all articles published up to and including the 31st of December 2023 were included in our initial dataset. Articles were screened according to specific criteria, which I will outline in detail later, resulting in a final dataset comprising 172 articles which yielded 248 distinct enrichment protocols. These protocols then became the focus of our analysis. The sample included enrichment applied across 55 different primate species. When we compare the relative number of protocols across the different families of primates, we find that some primate groups are more extensively studied than other groups. The Afro-Eurasian primates are more prevalent than the American primates, and hominids specifically are disproportionately represented in the literature. Notably, many primate families are not represented in the sample at all. The top 3 most studied species included in the literature were rhesus macaques, which accounted for 18% of the sample, chimpanzees, which accounted for 14% of the sample, and western gorillas, which accounted for just over 7% of the sample. When considering the conservation classification of the species in our sample, we found that most species were classified as least concern, according to the IUCN Red List, followed by endangered species and then critically endangered species. Together, these findings suggest that enrichment research is not necessarily targeting all species equally, or that priority is being given to specific species of conservation concern. The majority of enrichment research is being reported from zoo and laboratory environments, with a small number of protocols coming from rehabilitation and sanctuary settings. A small but notable number of protocols did not disclose the setting in which the enrichment was being applied. The lack of complete disclosure by authors in reporting aspects of their studies was a common problem found throughout the literature. Most of the enrichment is being provided to primates for long periods of time, allowing primates more opportunity to engage with the enrichment. A number of protocols applied enrichment for short periods, typically less than a day. This pattern likely reflects that some enrichment approaches are short-lived by nature, such as feeding or cognitive tasks, while others tend to be more long-term, such as enclosure modification or social interventions. Again, a notable proportion did not disclose how long enrichment was applied to their subjects. The most common enrichment approaches were feeding enrichment, which accounted for 23% of the sample, enclosure modifications, which accounted for 18% of the sample, and social interventions, which accounted for 13% of the sample. Our selection of protocols was based on whether we would be able to use the protocols to examine efficacy. In order to do so, we considered only those articles which described a baseline condition and used statistical analyses in order to determine the effect of enrichment intervention. For protocols which did not explicitly describe a baseline condition, the least complex, stimulating, or spacious condition was assumed to be the baseline. Studies which contrasted variations of an enrichment design were not included, such as studies which reported preferences of subjects for different food rewards or types of objects as enrichment. We also excluded studies which investigated spatial or social density manipulations, because primates actively employ specific strategies to mitigate the effects of such manipulations, and the welfare significance of these is unclear. Studies which investigated the removal of enrichment were interpreted conversely. We then extracted information for each protocol according to the following classifications, based on the baseline phase of the study, namely, the institutional context of the protocol, the species considered, the social conditions of the subjects at the baseline condition, the housing type, whether the housing was enriched or barren, how long the subjects had access to the enrichment, and the type of enrichment that was employed. Several enrichment types were considered and were identified based on their presence in the literature itself. Most are self-explanatory. Visual enrichment involved the presentation of uncontrollable visual stimuli, either in the form of images or videos. Both training and interaction-based enrichment involved heterospecific interactions, but the former was distinct in that it was intended to modify behavior of the subject themselves. Most protocols only used one measure of enrichment effect. Behavior was the most common and included decreases in abnormal or pathological behavior, decreases in aggression or self-narcotization, and increases in desirable behaviors, increased repertoire of behavior, or shifts towards a species-typical behavioral pattern as beneficial effects of enrichment. Physiological and clinical measures included decreased levels of stress hormones or inflammation markers, decreased veterinary intervention or treatment, and improved immune function as indicators of welfare improvement. Physiological and clinical measures accounted for the second most common approach to assessing the welfare impact of enrichment. Developmental measures considered species-typical physical or cognitive development. Neurocognitive measures indicative of improved welfare included improved cognitive function, increased neural complexity, and increased brain mass. We did also consider reproductive and survival metrics as indicators of welfare, but these were not present in the literature. 16 of the protocols in our sample use combinations of measures to assess their welfare impact instead of a single measure. When assessing our sample, we considered enrichment effects at a group level because most studies reported as such. In order to quantify the effect of each protocol, we applied a simple formula to generate a score of the efficacy of the protocol in question. Each reported measure was assigned a score based on an interpretive outcome as beneficial, neutral, or detrimental. If the measure indicated positive change in welfare, it was assigned a score of 1. If the measures suggested a negative change in welfare, it was assigned a score of -1. Where measures did not show any clear welfare effect, they were assigned a score of 0. As an example, a decrease in abnormal behavior and an increase in social behavior would be indicative of improved welfare, and each assigned a score of 1. An increase in aggression, however, would be indicative of deteriorated welfare, and assigned a score of -1, while no clear change in overall foraging activity would be scored a 0. These scores would then be summed and divided by the number of metrics considered, in this case 4, to generate a score representing the average welfare impact of the enrichment intervention. In this particular case, the score would be 0.25. We termed this score the efficacy index of enrichment, as represented by the equation shown. The index ranges from -1 to 1, reflecting an absolute deterioration or improvement in welfare respectively. Our index does allow for weighting of some measures, but in order to ensure the wide application of the index in the context of which we were working, we did not apply any weighting when assessing protocols in our study. Using our efficacy index scores, we examined possible predictors of enrichment efficacy. We first considered aspects of the species' biology and ecology in nature, which might impact on enrichment efficacy. We considered the enrichment type, the number of habitats the species occupied in nature, the family in which the species is classified, the maximum and minimum home range sizes, and maximum and minimum group sizes of the species in nature. Independently, we then considered influences within the captive environment that might predict enrichment efficacy, including the enrichment type, the institutional context, the social context of the application of enrichment, the type of housing of the subjects, the state of the housing, and the duration of the application of enrichment. These factors were investigated using two separate generalized linear models in R, termed the bioecology model and the captivity model, respectively. Only one factor emerged as a significant predictor in the bioecology model, namely the minimum group size of the species in nature, and two factors emerged as significant predictors in the captivity model, namely the enrichment type and the social context. When considering the minimum group size, there is a positive relationship between minimum group size and enrichment efficacy, such that species which naturally have larger minimum group sizes tend to experience more improvement in welfare following enrichment. However, the relationship appears to be relatively weak, suggesting that while statistically significant, it may not be as meaningful a predictor as some other effects. Enrichment type emerged as a significant predictor of efficacy scores, indicating that some enrichment types are more effective than others. This graph plots the mean efficacy score for each enrichment type, with bars indicating the standard error. Training enrichment emerged as the most effective, while interaction-based enrichment appears to be the least effective enrichment approach. Generally, enrichments which were more cognitively stimulating, fulfilled a biological need, or offered subjects a degree of choice or control were the most effective enrichment approaches. Curiously, social enrichment appeared to have an intermediate effect relative to other approaches. Finally, social context also emerged as a significant predictor of enrichment efficacy. When plotting mean efficacy scores for different social contexts, group-housed subjects appear to derive the least benefit from enrichment relative to other social conditions. A significant difference between efficacy in group-housed subjects and those either housed solitarily or under undisclosed housing conditions was found. These patterns suggest that enrichment may be most effective for socially limited subjects, implying that social interaction may act as a buffer against the stress of captive living. Our findings illustrate that there are several biases in the reported literature. Certain species tend to receive more attention than others, zoos and laboratories predominate, and behavioral assessment tends to be the most common means of assessing welfare effects. As with clinical research, there is an overrepresentation of studies reporting positive outcomes, and interpretation of studies tends to be biased towards a positive effect of enrichment, even when efficacy scores indicated diminished welfare. Regardless, enrichment appears to generate a net beneficial effect in subjects. All approaches consistently achieved positive index scores, with the possible exception of interaction-based enrichment. Few studies considered this approach, and so further research is needed into the efficacy of interaction-based enrichment. Control and choice appears to be important in determining enrichment effects, with greater efficacy scores emerging for enrichment which provided these. The social context also appears to be important when considering enrichment outcomes. Social conditions may directly impact on enrichment effects, and the natural social structure of the species may also play an important role in enrichment efficacy. The index we devised for our analysis appears to be an effective measure of efficacy. It provides a simple, intuitive, and adaptable tool that can be used to quantify how effective enrichment interventions are. In conclusion, enrichment appears to be beneficial to captive primates, but the efficacy thereof depends largely on the approach taken and the context of its application. There is a clear need for further research, as well as accurate, thorough reporting. Finally, our efficacy index provides a basic means for quantifying enrichment effect, which allows for comparison across a range of different contexts. Thank you very much for taking the time to listen to this presentation. I hope that you have found it informative. If you have any questions, feel free to ask them or to contact me via my email, which is on screen now.
Okay, I'm back. Wait. Thank you for this presentation, Luke. So let me check if we have questions already on YouTube. It's coming, I think. So I have a question for you. I'm not sure if I will be very clear in what I want to say, but what about the variation of the enrichment? Like, you can have lots of various enrichment for a species, but if the people on the team is using all the enrichment along the year or if they can just switch, it's like for kids, you switch the toys at some point, and it's like new toys all the time. You have less enrichment, but more variation in their enrichment. What do you think? Did you take this into account in the analysis, or?
So no, we didn't. We specifically omitted stuff like that for no other reason than it's very difficult to assess the efficacy of each individual component of that type of enrichment program. It's much simpler when you have a standard baseline that you can then compare against. So it gives you a very clean measure of how much of an impact that enrichment has had. It is somewhat unrealistic in that many institutions will do exactly what you've described. They'll utilize multiple different enrichments that will cycle from day to day and that kind of thing. But the intention behind what we did was really to try and identify the most effective approaches. So within the range of different options that we have available for captive primates, which are most likely going to generate a positive net effect at the end of the day.
Okay, thanks. We have a question from David. Does this effect vary over size of the community? Do larger groups gain more or less benefit from an enrichment?
It's very difficult to tell, to be very honest. We didn't include group size of the study subjects themselves as one of the predictors within our model. We were mostly focused on the sort of more biologically determined effects of group size. So in terms of the natural behavior and the natural ecology of the species themselves. So I wouldn't be able to say if there was a group size effect per se, but I would suspect that it would also depend very much on the type of enrichment that you're looking at. If it's something like an object-based enrichment approach, so for example, tossing in a ball, that can only be used by one individual at a time. There was one study that we looked at, which was done with baboons, where they were given the opportunity to forage from a single feeding device. What ended up happening was that male baboons would monopolize that device and basically exclude all other individuals in the group from accessing that enrichment. But curiously, what that ended up doing was it ended up bringing out appetitive foraging in the other animals. So the other animals would then go and engage in normal foraging, sort of searching behavior away from the device. So it ended up generating its own secondary effect of enrichment, which in itself is positive. It managed to manipulate the behavioral patterns of the animals in a positive way.
Thank you. We have time for one quick question. So from Amy, great talk. Have you considered interaction effects between the spatial biology-related predictors and the captivity context-related ones? So could some species respond differently to the same context?
It's very possible. We didn't really look into it in tremendous detail, but it is very much a possibility.
You have more questions, so I guess you will have to go in Discord to answer on Gather too. But thank you for this super nice talk, Luke. You can now leave the session.
Great, thank you very much.
Bye. And
Bye.
it's now time for a little break in the live session. So let's have a snack and join us for the session 2 of the poster. So do not forget to use Gather to meet the poster presenters directly. And see you in a few minutes, like in half an hour.